Okay, welcome back. So this is the second part of this e-lecture for XD3103, the planet Earth. And in this part of the e-lecture, we're going to talk about the atmospheres and the oceans that our planet has had. So we'll pick up from here.
So that was a little some thoughts about the core and that process. Now we'll think about the atmosphere and oceans, as I said, both plural. Okay, so the source materials for the planet we've already thought about. Effectively anything in the locality of the accreting centres, and in this case the accreting centre which will become the Earth. As this accreting mass is heated, the nebula gases, hydrogen, helium, work their way out of the solid, maybe melting mass. The tiny amounts of methane and water also work their way out. And these form our first atmosphere. This process of potentially melting and chemical liberation and permeation of gases and melting of ice to get liquid water is called or termed sweating out. So these substances began to be sweated out of the juvenile planet. Now, there are some slightly interesting takes on this process in terms of the way I've described it, in terms of the noble gas isotope data and the hydrogen deuterium isotope data, but we'll talk about that a bit later. So that's all fine, and that first atmosphere that our planet had was called the primordial atmosphere. That's all fine, it forms. Now, at some point soon, the amount of matter which is accreting around the body which will become our sun, our protostar, gets high enough that the force of gravity in the centre of it is strong enough to actually force an atom of hydrogen and an atom of helium together. That process is called nuclear fusion, and when you do that, you release an awful lot of energy. I'm not going to talk in this module about fusion and fission. If you're chemists, we'll talk about that much more at level 4. But nonetheless, it gives out a lot of energy, a lot of heat. So as soon as this starts happening, the star gets, or the protostar gets dramatically hotter, it lights up, it becomes a star. And that's how our sun was born. Now, during this process where the primordial atmosphere is formed and continuing to be formed, our star lights, and apart from, because it's hot, it's bright, it shines electromagnetic radiation, including visible light, gamma rays, X-rays, radio waves, out, it also streams protons out from it all the time. It's called the solar wind. And that, our first primordial atmosphere, effectively got blown away by these charged particles. So our first atmosphere, our primordial atmosphere, we lost it as our new star lit. So the solar wind, unfortunately, well, actually, very fortunately, blew it away. Before that event, it was in darkness. There wasn't too much chemistry. After it lit, basically electromagnetic radiation is energy. This is h nu, a photon of energy, and molecules can absorb under certain circumstances that energy, and then you get chemical reactions occurring. Now, what I'm about to show you is highly speculative, and it's based on the upper Jovian and Saturnian atmospheres that we currently have in our solar system. But it's probably not too far from the mark, because actually there is no reason to think that these substances weren't there as they are in the gas planets, which effectively have nebular atmospheres. So, the thing to emphasize here, very, very speculative. It was dark, remember, when our planet started accretion and when the primordial first atmosphere sweated out. So if we look at these elemental cycles for hydrogen, carbon, nitrogen, phosphorus, we have good spectroscopic evidence for the presence of these types of species in the upper atmosphere of Saturn and Jupiter. Therefore, we have no reason to think that they wouldn't equally have been in this early primordial atmosphere. Now, h nu, where you see it, is a shorthand for a photon of light. So if the sun is not yet lit, these paths will not really run. So if you look again at these cycles, so you've got hydrogen molecules going to hydrogen atoms backwards and forwards. You've got effectively carbon present as methane, because there are no forward paths here which would proceed without photons. You've got nitrogen, a bit more interesting, losing hydrogen and then going back again. So again, your pool is ammonia, but some of the NH2 can combine with another similar molecule, and you can end up with hydrazine, N2H4. And similar stories for phosphorus. So it's a very simple system without light. Put the light on, the star lights, and suddenly you have a more active photochemistry. Now, clearly you have the active photochemistry only as long as the atmosphere is still retained. Remember, the whole issue here is that solar wind has blown this atmosphere away effectively. So it was nice while it lasted, I think probably would be the way to put it. Okay, so let's come back to our thinking about that very first period of the Earth's geological history, the Hadean, from the word Hades, for hell. So in the beginning, it was hell. We've talked already about the type of accreting Earth, heating. You've got the melting event to give the core. You've got what was in the accreted body, the gases effectively being sweated out, waters, the ices and things will have melted and then worked their way out through the accreting planet, and various chemistry going on. We've talked about the atmosphere. We won't talk about that anymore. We should talk about that very early primitive ocean. Now, clearly it's a broth. It wouldn't look much like the ocean that we know today. It was very reducing, lots of hydrogen in it, elemental sulfur, sulfides, metallic iron. Anything even vaguely soluble would have been in there, so you'd have plenty of ammonia in there. But it was still basically water. And you might ask, well, hold on a minute, where has the water come from? Well, you might be interested to know that most molten silicates, lava, often you can get 80 grams per kilogram of water dissolved in that molten lava. So in fact, there was plenty of water. It literally, now you see the term sweated out, both for atmosphere and ocean, but that's very descriptive of the type of process that was going on. So yes, you had oceans, you wouldn't recognise them, and they wouldn't be over vast areas of the planet, because general consensus is that there were areas of the surface what was it like, which actually were open lava. You had molten rock, areas which were cooling and thickening, and obviously it's here that you're more likely to start getting your water forming. But it was hell. Incoming meteorites, massive volcanism, outgassing. You probably had a primitive hydrological cycle running, so that water was evaporating, moving away from the planet, cooling, condensing, and eventually falling back as rain. As this cycle goes round, you're actually pumping heat away from the surface, which allows more of the surface to cool. So that was the Hadean, and we move on through the Archean to the Proterozoic. Interestingly, at times, probably later, probably in the Proterozoic, but the surface here is very hot. There were times when there is reasonable evidence that probably the entire surface, or the vast majority, cooled, maybe as low as -70. There's a minus sign missing there, apologies. In parts. This idea that snowball Earth, the model that actually the temperature excursions were large as you formed an atmosphere, then began to modify that atmosphere. Yeah, there wasn't very much in the way of temperature control, and we'll think about that in a moment. So, yeah, it was interesting times, as both the Scottish and Chinese expressions would say, and we can't know exactly, but fossil evidence, in this case isotope and mineralogical evidence, tells us that there was lots going on. Okay, we've talked about the chemistry of that primordial atmosphere, and we've done a little bit of description about the chemistry or the character of that primitive ocean. We're now going to look at the primitive atmosphere, which was the second atmosphere the planets had, and then we're going to go back to the oceans and look at the processes that went on in the oceans, actually, which drove some of the other changes. So, our primordial atmosphere has blown away. We're now thinking about our primitive atmosphere, which was the thing that replaced it. I should take you first through this table. The colour coding here is the green planets, and we've got other solar system objects here other than just planets. The green type of bars are, if you like, the terrestrial planets, the metal planets. The pink planets are the gas planets. Remember, there were two types of planets, two types of process that formed them, and actually two types of atmosphere. I'm going to talk about the Earth's atmosphere slightly separately at the moment, which is why I've coloured it blue, so I'm not thinking about that. Instead, I've done a calculation of the Earth's equilibrium atmosphere. So you could predict, in the absence of anything else, that the atmosphere of any given planet would be in some sort of thermodynamic equilibrium with the materials which form the planet. Now, we have two types of atmosphere from two types of planets. You've got the gas phase planets, the pink ones. Mostly it's nebula type material, a bit like our primordial atmosphere. Then you have the primitive atmospheres of the terrestrial planets, somewhat different. Let's look at the gas planets first, and you can see that the atmospheres are pretty similar in terms of composition. 90% hydrogen, bit of helium in there, tiny amounts of water, and so on and so forth. The green atmospheres, you can see much less hydrogen, tiny amounts of hydrogen. You've got maybe a bit more water. You do have, however, lots of carbon dioxide, lots of nitrogen, mostly. Or at least on Titan you've got lots of nitrogen. And I'd like to come back to that. But certainly on the other planets, some nitrogen. So, composition-wise, the green ones look very, very different from the red ones. Nitrogen on Titan bears remarkable similarity to nitrogen on Earth. Bookmark. Okay, right. So the primitive atmosphere then, one can expect it to look like this on Earth, very related to the atmospheres of the other primitive terrestrial planets. Right, now I guess what we need to think about a little bit more is what happened next. Because this blue band is the current Earth atmosphere. And to make the point rather clear, this is the current composition on average of the Earth's atmosphere, and this is the if you like, the primitive atmosphere. So effectively the red is the modern atmosphere, the oxygenation atmosphere that we have. Now obviously what happened, I say obviously what happened, we'll look at it more in a second, is that life happened. Life did a lot of this processing that's changed our atmosphere from the primitive to the modern. And in fact, a very famous scientist, Professor James Lovelock, he used this, he was working for NASA at the time, and he used this very fact to say, guys, we don't need to go to Mars to look for life. Because if life were there, then the Martian atmosphere wouldn't look like the other primitive atmospheres in the terrestrial system. It would look more like Earth's atmosphere. You can imagine that that didn't make him very popular with NASA. However, the observation is good. Whether or not there is life on Mars, it is now broadly thought that there is low-level life on Mars. We haven't actually found definitive evidence yet, though. But if there is, it's of a volume and a magnitude that it hasn't effectively done the sort of planetary engineering. Mars is fascinating, actually. It's got a core, rather like the Earth. Unfortunately, it's rather small, much smaller than the Earth, which means the core cooled more quickly. But it's clear from Earth that there was liquid water on the surface. You can see the landform evidence. So Mars is interesting, and we'll talk more about Mars and life when we talk about Earth and life in a moment. So, in terms of the atmosphere, we've got primordial, which we've looked at, primitive, which I've calculated here effectively as an equilibrium atmosphere, and finally modern. And I've said that life made the change from basically took a primitive atmosphere and by its actions and products formed our modern atmosphere. I should probably make good on that now rather than just asserting it. Okay, there's a summary. So let's now look at what changed, what that change was. Because if we look at not only the atmosphere actually, but the geology of the Earth, it's clear that whatever this process was that I'm calling life actually took the overwhelmingly carbon dioxide atmosphere and converted it effectively to limestone, took the carbon dioxide out of the atmosphere. So the changes are more than just the atmosphere and the ocean, but I know in the geological part of this module you'll talk a little more about those. 5 billion years ago the planet formed. Only 200 million years later, which is a very short time, you have an equilibrium atmosphere which is very rich in carbon dioxide. If you do the sums, you're going to have a pressure on the surface of about 100 atmospheres. There is maybe some evidence of water. Okay, now we're at 4.28 billion years before present, so you're still just about the Hadean. Maybe you might want to call it the Archean, but you're still very, very early in Earth history. This piece of rock is actually from Hudson's Bay in Canada. It's what's called a mafic rock, and you can see there are all sorts of inclusions in there. The fact that this is mafic means that you've got water on the surface. This sort of rock needs water to form. So suddenly at the end of the Hadean, where we've been thinking about volcanism and we've been thinking about lava, in some areas of the planet the temperature must be less than 100. You've got rocks forming in water. So this is the first stage of the very interesting story of what happened next and what changed. 200 million years is very, very fast indeed. And certainly the 2008 science paper makes fascinating reading. Okay, we've actually got evidence in the form of zircons, which are minerals which form under acidic circumstances. We've got evidence of zircons at 4.4 billion years before present. So there was some water in some areas on the surface 200 million years ago, even before the mafic rocks were formed. But we've got the formation of zircons. You can imagine that we've got tectonic, since the core formed, the tectonic system ran, subducting ocean crust as carbonate, so CO2 was being reduced by purely geological processes, and by 4.26 billion years before present, we've got alkali rocks in India. So acidic at 4.4, alkali at 4.2. Now, obviously, these numbers are approximate, but nonetheless, this tells you there were significant changes going on in the surface environments of the Earth, because you've got to remember, it wasn't one environment. There was a whole hodgepodge of different environments. Some you still had molten lava at the surface. Others you had relatively cool water. So, yeah. Then comes maybe the bombshell. 3.8 billion years before present, you have black shales. Now, they're from Greenland. The fossil evidence is from rocks which are now in Greenland, you understand tectonically that things move around the surface of the Earth. And that evidence is really interesting. Black shales effectively mean sulfur-based photosynthesis, not oxygen-based that we have, but sulfur-based. The atmosphere was very, very reducing, and clearly this happened in the ocean part of it, so the ocean was very reducing, with lots of hydrogen sulfide, elemental sulfur, elemental carbon, ammonia, carbon dioxide maybe, iron, lots and lots of very reducing environments. Nowadays, if you were to take a bicycle, let's imagine it's made of iron, and throw it into the sea, it would go red and rust. The oxygen would be reduced, and the iron would be oxidized. An oxidating, oxygenated ocean. If you threw a rusty bike into this ocean, the opposite would happen. The oxygen would be taken out, the iron oxide would turn back to iron. So the chemistry is fundamentally different. There are still reducing environments on the planet, somewhat more like refugia, but we'll talk about those any moment now. The big point is 3.8 billion years is very, very early indeed. So, almost as soon as parts of the planet are cool enough, and crucially, that you have surface water, when we see fluvial fossils, evidence of fluvial water, flowing water, then you start seeing these life fossils as well. So we've had to rearrange our ideas quite a lot about how quickly life evolved. Now, bear in mind here, we're talking still about what changed. We're at 3.4 billion years before present. We've got plenty of fluvial rocks around, fluvial fossils around, so we've got plenty of running water, and we start seeing effectively fossils which look a lot like oxygen photosynthesis. Temperatures in some places still about 70, other places lower, but that's fine for modern thermophiles, modern bacteria that we see that can that live in submarine volcanic plumes, for instance, are quite happy at 90 centigrade. So now, as many people have said to many other people under different circumstances, this is a bit quick. Yeah, as I said, looks like life was a bit quick. And here is to remind you the geological timescale. So effectively here is where Earth history started. The core formed about there, and very, very rapidly indeed you have these fossil formations where you have the black shales, and you have the so-called Australian formations from Australia. And here are some pictures of those formations. And you can see very, very clearly that you have things that look an awful lot like bacteria there. You have stuff that look a lot like modern photosynthesizers there, blue-green algae and stuff like that. So this was the type of change that happened. And oxygen photosynthesis, if this is I have a curriculum vitae, literally translated a timetable of my life, as you do. But this is the CV of life itself on this planet. And you can see very rapid. Certainly by 3.5 billion years BP, we had oxygen photosynthesis, and I'm going to take you through some of the proof of that and some of the evidence. If you think about the situation where this oxygen photosynthesis or these organisms came into being, we've already said very reducing lots of iron, hydrogen sulfide, reducing oceans, reducing atmospheres. So what would happen to that oxygen? Well, the moment you form oxygen in that sort of marine environment, it's going to, and here is an example with iron sulfide, you're going to get oxidation of your iron sulfide, in this case up to iron sulfate. So you've got plenty of light there, you've got plenty of nutrients for these organisms. This is going to start happening, but you're not going to see the oxygen initially, simply because that oxygen is being consumed immediately by the surroundings. What I'd like to do is to show you an example, if you like, of what happened, and then I'm going to show you some of the evidence. Okay, so he's gone mad, they're all thinking. A titration is the model that I'm going to use. So in this titration we have an alkali in the conical flask, an acid in the conical flask and an alkali in the burette. Maybe it's hydrochloric acid in the flask, and maybe it's sodium hydroxide in the burette. And you remember, you add your alkali, you've got an indicator in here. Where the jet hits the surface, you have the pink colour where the indicator is in an alkali environment, but as you mix it back through the solution, then the acid takes over and it returns to colourless. And it's one of the things when you do a titration, one of the really important reasons or observations that you can make when you do a titration, so you don't overshoot it, is you add slowly, and gradually as you get closer to the end point, the pool of colour that forms where your burette jet hits the surface stays for slowly longer. And that's how you don't overshoot a titration, because that will tell you as you get close to the end point that you are getting closer to the end point. Anyway, so our titration, so you add, in this case, your sodium hydroxide, a bit at a time, you swirl it round, and most times when you swirl it round, it goes colourless again as the alkali is consumed by the surrounding acid in the flask. But at some point, you swirl it and it doesn't go colourless again, which means you've just added, from the burette, you've added just the same amount, you've added the amount of alkali to exactly neutralise the amount of acid that was in the flask. And then you do various calculations from that, volumetric calculations, which I won't bore you with. A titration was exactly what was happening in that early ocean. Except if it were in a flask, brown will be the colour that it would end at. So, what I'd like to do now is show you what the evidence is, but let's first explain the mechanism. So, back when we're talking about the evolution of oxygen in the primitive ocean, in the burette, if you like, is the oxygen, and in the flask are the primitive oceans, the primitive seas, reducing, full of iron and stuff like that. You add your oxygen, and in this case, what you get is a brown colour, because your iron oxides, what you get is a black colour, because your iron oxides are black. Or you can get a red colour, because some of your iron oxides are red, like for instance in rust. So it's a titration in terms of the way it happens, except life is producing that oxygen, and as it produces it, it reacts, and at some point the titration is finished. This is a picture of what are called banded ironstones, and if you go back a little in the geological calendar, back to the time that we're talking about here, so we're maybe 3+ billion years before present, you see geological formations like these. So where we are is we get the formation of banded ironstones, so-called, black, sometimes silvery colour, and red bands, giant formations, which effectively show you what was going on in the oceans. These were precipitated as reaction products of this titration. This is a picture of Blaenavon in Wales. There are some spectacular banded ironstones here. I mean, yes, there are banded ironstones basically all around the world, or it's certain places around the world if you know where to look. But yeah, these places, as a young man, I walked and lived part of my life, so it feels very familiar to me. But you can see the brown colours. Okay. We move on. We've got banded ironstones being formed, the titration is happening, you've got effectively oxygen, photosynthesis, cyanobacteria. Now, it's a big world out there, it's a big ocean. What was happening in the oceans while this oxygen was being produced and forming those beautiful red ironstones, bands of ironstones? What was happening is the inhabitants of the oceans, which up until that time had all been anaerobic, and we still have refugia, we still have survivors of that time, these anaerobes, these ancient organisms. Nonetheless, in the majority of the ocean, where this poisonous gas oxygen was being produced by this new life, those organisms were dying because they can't tolerate oxygen at all. So for the next maybe billion years of Earth history, actually what was happening was the ancient ocean, the primitive ocean, was being slowly oxidized into our modern oxygenated atmosphere. Now, this is an unimaginable amount of time, but you've got these organisms, they've got plenty of food, they've got plenty of light, they're just going for it and slowly colonizing, and the amount of oxygen being produced was huge, but it was being consumed in the titration, forming our banded ironstones. But at some point, about 2.5 billion years before present, the ocean was then oxygenated, it was oxic. At that time, this massive production of oxygen didn't need to be used in the ocean anymore to oxidize it. It hit the oceans. And anything on land, maybe in puddles or whatever, would have been anaerobic. There was a mass dying then of the non-ocean anaerobes. We think about air pollution now, but trust me, this was probably the largest air pollution incident that's ever occurred in Earth history. And now that massive oxygen production, which has oxidized the oceans, then transforms the atmosphere, and it becomes the modern oxic atmosphere that we know. So you see, the history of the atmosphere and the oceans chemically are really quite closely intertwined. Okay, so we wanted to think about the evolution of the atmospheres and oceans, and here is a modelled graph from Richard Wayne's book, The Chemistry of the Atmospheres. Goes back to about 4 billion years, and the slow growth of oxygen. And as the oxygen increases, the complexity of organisms increase up until now. This scale is interesting. It's the log. No, well, okay. It's a decadal magnitude scale of present atmospheric level of oxygen. So 1 is the present atmospheric level of oxygen. Notice, if you will, that we only reached the present atmospheric oxygen level about 300 million years ago. That's relatively not very long ago, and it was only then that you started getting land mammals. Okay, let us move on. Yes, okay. I couldn't resist this. Anyway, away from growth of oxygen and growth of ozone and the ozone layer.
Okay, so this is probably a good time to end this portion. So we've started at the beginning, we've gone through the original reduced atmosphere, we've looked at the impact of life on the equilibrium atmosphere and how that has eventually got us to our current oxic atmosphere, which brings us up to now. So in the next final part of this lecture, we'll be looking at the modern planet, modern atmosphere and oceans. Anyway, thank you very much. Take care and see you in a minute. Bye bye.